This is the first of our fall seminars for bsac. So we hope that you will be able to join us for all the other ones coming up, and you can go to the bsac website to see the schedule. We have a collection of external invited speakers, as we're starting with today, and also some student presentations where most of those will be a very short presentation and then an open discussion. And the idea of those student sessions will be to get feedback from other research groups, not just their own, about their project, about things that they have questions about or advice that they want to give or whatever. So very interactive for those student sessions. But we are also going to have some very interesting and I think a lot of fun external talks coming up too. So hopefully you'll join us for that. For the people online, I just want to mention that if you have any questions during the talk, they will be captured. I will be monitoring them in the chat window that's next to the video screen. You know, those of you who are online are viewing this over YouTube. So just type in your questions there, and then we'll collect those, and the speaker will answer them at the end. But for any of you here in person, the speaker can either answer them as they come up, or you can wait till the end, whatever your preference is.
Yeah, either way is fine.
Okay, great. And with that, I'll turn over to Professor Lin, and he'll introduce our speaker.
Good. I will just have a very short introduction for Ashwin Seshia. Ashwin is actually one of the bsac students back in, I think, from 1996 to 2002. So one of you guys here, when he was a student here, he got his bachelor degree IIT Bombay in 1996, master and PhD degree in EECS here, UC Berkeley, 1999 and 2002. And he has been with Microsystem Technology at the Department of Electrical Engineering and Computer Science at Cambridge University. He has many awards, including like IEEE Fellow. And today he's going to present his work on vibrating beam MEMS accelerometer for gravity and seismic measurement. Welcome.
Thanks. Yeah, and thank you all for coming, and good to be back in bsac and with close friends. So what I'm going to talk about today is a journey I've been on for many years, and I want to share some of that with you. In part, it's a journey about technology that I've been involved with, including going back as a student at bsac. And it's an area that I think most of you in this audience will be familiar with, MEMS accelerometers, but applied to a domain that's not traditionally associated with accelerometers. So to gravity and seismic measurements. And it's also in part a story about this spin-out company called Silicon Microgravity that I established maybe 6-7 years ago. That's commercializing this technology, and I'm going to tell you a little bit about what the company is doing, and yeah, some of the challenges and interesting applications that are being addressed. All right, so gravity, and we all take gravity for granted. And this is an interesting sort of depiction of gravity field anomalies on the surface of the Earth as mapped by the NASA GRACE mission. The NASA GRACE mission had a set of twin satellites in Earth orbit looking at measuring gravity to a high level of precision to infer, for instance, aspects to do with the melting of polar ice caps and such, because these are measurable effects. So gravity can be used to infer a lot about a planet, and has been used, and instrumented in the past, though in a very limited setting. So what's being plotted here are in fact gravity field anomalies relative to a featureless surface. These are plotted in units of a gal named after Galileo. So that's a centimeter per second squared. So for those of you perhaps more familiar with MEMS inertial sensors, that's about a milli G, roughly. And you can see the anomalies here that vary between -50 to +50 milligals just because of the terrain and aspects that have to do with differences relative to a featureless surface. Now, if you get to 3 orders of magnitude below that level, you can start to infer much more fine detail about the subsurface, and that's part of what I'm going to be talking about today. Okay, so principles and historical development, these instruments have been around for over a century. And in fact, the physical principles that are associated with measurements of gravity haven't changed a whole lot. And the instruments that are industry standard instruments today are still based on mass on a spring, measuring the offset position of a mass under gravity, and absolute gravimeters based on free fall instruments. And historically, oscillations of a pendulum. And of course, from high school's physics, you could relate these things to the measure and being gravity, gravitational field strength, to things that you can measure, changes in time of fall or displacement and such. But if you look on the right, this was a trip that we undertook to test our gravimeter in a basement facility at the British Geological Survey. And you can see the free fall instrument here on the right. So you just get my laser pointer on. So that's the free fall instrument there that's still being used. And this is the mass on a spring instrument. These are still bulky, fragile, often difficult to use instruments. The instrument here, the mass on a spring instrument, that's the most commonly used gravimeter for field use today, costs upwards of $100,000 or so. So these are not necessarily easy to access. There are issues with robustness of use, and particularly in harsh environment scenarios, which is one of the reasons we got involved as well. But there are lots of interesting applications of gravity, including going beyond our planet. So the earliest Apollo missions had this astronaut here carrying a 15-kilogram instrument, a gravimeter, that was based on an approach that's very similar to what we've instrumented at a MEMS scale. So it was a vibrating string accelerometer developed out of MIT Draper. And they were able to do the first sort of gravity measurements on the moon to figure out the nature of rock at the location that the survey was undertaken. So it was considered important enough as a suite of instrumentation techniques at the time, and continues to be even to the day. So this is a science paper published a couple of years or so ago that was the first gravity traverse on Mars. And it was done by repurposing the accelerometers in the Northrop Grumman IMU that was built in for the Curiosity rover, and correcting the accelerometer outputs to be able to get down to the to a measurement of gravity. So it was a relatively crude measurement because these weren't purpose-built gravimeters, but comparable to the measurements that were undertaken in that first lunar mission. So on the level of about 10 milligal of accuracy or so, it still gave valuable information about the density of rock in Gale Crater where the rover was moving around. And so a technique to read into what's below the subsurface without being invasive about how we probe that subsurface. And the instruments I'll talk about to you today will have about 3 orders of magnitude higher resolution as compared to these. And this is one of the reasons we started to talk to colleagues at Johns Hopkins and at NASA. This was a paper that we presented at the AGU fall meeting. So the last time I got out here many years ago, talking about what we could do by combining in a compact MEMS instrument, a gravimeter and a seismometer, that might go out to the moon and provide valuable information about what's underneath the surface. Gravity measurements can be used to infer density contrast. Okay, so they can tell you the what's underneath the surface, and if you've got a dynamic process where things are changing, it can tell you a little bit about what's happening there. And that's actually the first application we got involved with. So this was about 12 years ago when we undertook a project together with BP Alternative Energy to look at CO2 sequestration monitoring. And CO2 sequestration monitoring is considered to be one of the suite of technologies that's relevant in the context of climate change mitigation, where you're going to be pumping many hundreds of kilotons of CO2 into, say, depleted underground reservoirs or producing reservoirs where there's co-production, as shown here. And what's happening is that CO2 is displacing, say, water or gas. And so as it does so, there is, of course, a contrast in the density of the CO2 relative to what's already there. That mass redistribution can be measured if you have a monitoring well, say about 100 to 200 meters away from an injection well. And as I'll show you later on, you can model these processes and show that these effects are just as measurable as the effects of earth tides on a monitoring instrument. And this is relevant because if this is to be one of the technologies that moves forward, then effective monitoring of the CO2 over long time scales is absolutely essential. So you need to have some way of monitoring that the CO2 that's pumped underground remains underground over decades. The other application, this is in collaboration with a colleague at the Colorado School of Mines who's done some work on groundwater monitoring using gravimetry. And this is a map from the US Department of the Interior showing the potential, this was well over 15 years ago that this was put together, the potential for conflict over water and the areas that are at the time considered to be most at risk. And one of the proposals that's in this paper is to take, for example, be able to repurpose abandoned coal mines or actually occurring underground aquifers to get the water from in the winter months into those areas, store them, so you're not minimizing land usage, surface land usage, and then you've got to find a way of monitoring the water levels over time. And this can be done as well using gravity. So this was the survey done, the survey points shown here, and also modeled the gravity differences that were measured over a certain time period from the early summer months to so over this sort of 10-month period. And you can see levels in the hundreds of microgals that are measured on changes in water level in that time period. So if you could build an instrument that's sensitive enough, and obviously, these are fairly tedious measurements that are done right now with a single also instrument that's taken out manually to different locations spread out over kilometers. And at each sort of location, there's a reading that's taken over potentially, half an hour or so. So these are fairly tedious measurements that are done today. If you had a low-cost gravimeter, you'd have tens of thousands, obviously with MEMS monitoring continuously, then that reporting back, or something that's on a moving platform or a rover, that changes things considerably. So the other half of what we were looking at was seismic. There were MEMS seismic devices back in the time. This is a slide from Sandia from about 10 or so years ago. We were undertaking this project with a bar on this showing the best commercial MEMS at the time. This vertical scale is in units is noise floor in G per root hertz or in meter per second square per root hertz. Take your pick. Over a frequency bandwidth going from 10 to the -2 to 10 to the +2. And what's fairly obvious and is plotted against the earth noise models, the high and low noise models, just the geophysical natural noise of the earth, against macroscopic instruments that are pretty big when you compare it to one of us, right? So the most insensitive instruments, again, have the same issues that I talked about macroscopic gravimeters, but they are extremely low noise instruments that cover this entire band. Best commercial MEMS tends to tail off because of low frequency noise and drift at that time. Of course, things have improved, and part of what I'll show you right at the end of the talk is a MEMS device that's got a flat noise floor right up to 10 to the minus 3, all the way to over 10 to the plus 2, below what you have here today. Okay, so to understand the limitations at the time, we've got to go back, and have a look at some very basic first order analysis of a capacitive MEMS accelerometer and understand where the limitations are arising from. You look at mechanical sensitivity of a capacitive MEMS accelerometer, the gradient of the displacement with respect to acceleration, it's inversely proportional to the square of the natural frequency. So that's a fundamental scaling law. And if you want to make a very sensitive device, you've got to decrease the natural frequency, either by increasing the mass or decreasing the spring constant, both of which are counted to miniaturization. So the most sensitive MEMS devices tend to be about a couple of centimeters on a side, and usually are heavily engineered, and there are heroic attempts to reduce that natural frequency to 10 hertz or below, but it's usually a one-off device. For example, one might be sent out to Mars. There is also the other limitations. When you build such low natural frequency systems, they tend to be more susceptible to shock, have issues with robustness, handling. There's also limited dynamic range. So you can't measure, we're in the background of 1G. If you want to measure down to 1 nano-G, that's 9 orders of magnitude in dynamic range. So even with force feedback, that's difficult. So the most sensitive gravimeters tend to have a upper end that's about a milli-G or so if they're going down to a nano-G. And susceptibility to low noise, low frequency noise and drift. You're essentially trying to pick up a DC signal. Gravity is a very low frequency measurement, and you can be susceptible to drift that impacts systems that are based on masses and springs. Okay, so as opposed to this, a resonant vibrating beam accelerometer operates as so. So you have a proof mass where the inertial force on the proof mass, say, due to gravitational loading, is coupled to say, vibrating beams. And in this particular configuration, you've got the beams changing frequency, one that the frequency increases, the other decreases, because one's subject to tensile and other compressive loading. And it turns out that, first of all, this measurement can be done at a frequency that's hundreds of kilohertz, for instance, so well above the noise corner of off-the-shelf electronics. And also, essentially, you're measuring a frequency difference. And so you've got a suite of very precise measurement techniques you can apply to that. There's been a lot of development around MEMS clocks that directly impacts on understanding the frequency stability associated with these systems. The other thing is the scale factor that I touched upon with the capacitive device. If you look at the scale factor, this is a ratio of, there's a material constant, the volume of the proof mass divided by the width and thickness of the tines, if it's vibrating in plane. And so it's scale invariant. There is no direct conflict between mechanical bandwidth and sensitivity. So these systems could have a primary natural frequency of a kilohertz or so, and still provide comparable sensitivity to the displacement of the device. Yeah, go ahead. Yeah. So this is showing, one of, so you can operate the beam in a number of different modes. And the higher order modes provide you a higher sensitivity to axial loading as compared to the lower modes. So in this particular case, we're operating the beam in the next, so it's not the fundamental flexural mode.
Frequency goes up, and then or the other way, and the other one.
Yes,
You check out
that's correct. Yes,
it's a function of how much displacement you have.
that's correct. Yes, yes. So you've got electrodes on the outside that pick up the displacement of beams capacitively. It's a straight beam, precisely. It's a straight beam. Yeah. Right. So interestingly, the first vibrating string gravimeter was reported by Gilbert, who was based out at Cambridge, and back in 1949. So this is in the proceedings of Physical Society B, or Society B now. And it's in that paper, this gravimeter, which consisted of a mass and a vibrating wire that was stretched against the mass. And this whole thing was evacuated. Aspects around vacuum encapsulation and such. And this particular device then was the first gravimeter used in a borehole environment. A version of this was instrumented later on by Bosch Arma, that became the basis of the MIT Draper vibrating string accelerometer and so forth. So this principle, of course, has been around at the time at the macroscopic scale as well. And these readings were actually made on a submarine where this gravimeter was being run relative to a pendulum gravimeter. And so this paper reports the relative error between the two readings on the order of a few milligals, which was the level of precision at the time. Running things on submarines were of interest because in those days, inertial navigation wasn't as precise. And so gravity-based maps, particularly for submarines, were considered of interest for navigation applications. All right, so the other sort of half, so that was a transduction technique that's been around for some time. We, around the same time, started to look at other transduction principles that would get us the very high sensitivities and high stabilities at the same time. And this principle called, we dubbed later mode localized sensing, that's closely related. And it consists of essentially a coupled mass spring system. So you've got two resonators that are weakly coupled and ideally nominally symmetric. So, an analogy to coupled pendula, weakly coupled pendula, you'd have, in this particular case, two modes of vibration, in phase and anti-phase mode, both symmetric. The system was symmetric. And the idea is to couple in the measure end as a break in symmetry. So, for example, the measure end would perturb the spring constant of, say, one of the resonators. And it turns out that in a principle well established that's related to localization in other contexts as well, but vibration mode localization is the term in structural dynamics. You essentially end up confining the vibration energy to one or the other resonators, and this is reflected in the change in the mode shape, which can be practically measured by just simply recording the amplitudes of motion of the two beams. And this is something you can simulate in a program like COMSOL, for instance, changing, say, one of the parameters just a little bit. And it's an extremely sensitive readout of that level of asymmetry between the systems. So if you say undertook a perturbation-based analysis, you can show that the shift in eigenstates, the fractional shift in eigenstates, is proportional to, say, the change that you're trying to measure, the change in stiffness on one of the resonators, divided by the coupling spring constant. So the weaker you make this, the stronger the localization effect. And in contrast to frequency shift-based sensing in the same system, the difference is a ratio that's related by the strength of the nominal springs to the coupling spring. So the fractional changes in the output metrics can demonstrate very large levels, orders of magnitudes of levels of differences in relative measure. Though, of course, amplitude measurements and frequency measurements are two different things altogether. Now, common mode rejection is the other reason we looked at this, because really the output metric is impacted by changes in symmetry. So if you've got a common mode effect like temperature that impacts on the parameters in just the same way, then to first order, you shouldn't see any differences in the measure in the output metric and the eigenstate. So if these were very closely located, they're seeing exactly the same conditions, then ideally nothing changes. So that was the other reason that this is a compelling method to look at. Yeah, go ahead.
If they're right in the same location, they could measure the same gravitational force. You don't get it signal. How do you separate? How do you get one that feels gravity and another one that doesn't?
Yeah, and that's exactly. Yeah, that's exactly where I get to here.
Oh, okay.
So these are showing you versions of how this could be applied to the implementation of an accelerometer. So you would still have, say, one of those resonators coupled to the mass, but the other isn't. It's just co-located. You just get rid of the mass. So you then dial in a specific sensitivity to that. That breaks the symmetry. So it can be, also, the same system can be read out as frequency shift mode or an eigenstate readout, both. Okay, so let me now get into the results. So our first devices, sorry, next one. The lower left is an SEM image. Yeah, so the question was, what are we looking at here in the lower left image? And the lower left image, this is out of a MEMS paper that we published some while ago. And it talks about, what we just discussing, how do you instrument this in a way that would give you a meaningful readout of acceleration, for instance. So what you got here is a suspended proof mass that's linked to one of those resonators. And in this particular case, I think it's capacitively linked. So there's a change in the electrostatic spring constant. And the other resonator is coupled to that primary resonator, but not coupled to the mass. So that's what's here. It's sort of a very simple proof of concept demonstration.
And how are you reading out the resonance?
So what we typically do is to close a loop on one of the resonators and then measure the amplitudes of motion of the two resonators independently through two independent, say, readout channels. That's a proxy for the eigenstate measurement. Using, just measure the motional currents from the two to the two resonators. So that's just.
Where's the? I don't see an input or output.
Yeah, this is just an SEM image with some bond wires sticking out. So that there's this input here, which dials in a force to this mass.
That's an electrostatic gap.
That's an electrostatic gap between those two. Then there are these ports down here, which are electrodes being connected to the resonators to actuate and detect their motion. But
Capacitively, thermally?
Capacitively. So there's a device later on that gives a lot more detail. So this was an early proof of concept device, which with the SEM I can see. So that the coupling between the two was electroelastic, which is just an electrical spring, right? But they weren't mechanically coupled. And you've got an electrode here, which is sort of capacitively driving that one. You'd have another electrode coming in from the other side to measure the motion current. So it's all capacitive.
Parallel plate.
It's parallel plate, yeah, precisely. there's a more detailed device micrograph that I'll get to that shows a lot more. So with the MEMS VPA, this was implemented in a standard SOI MEMS technology without any vacuum encapsulation at the wafer level. This was at the die level, and to test the sensitivity to gravitational loading, the very simplest thing to do is to mount this on a controllable tilt platform and orient the sensitive axis relative to the vertical. Okay, so you just have different components of gravity acting along the sensitive axis, and so you should trace out a nice sinusoidal response as a function of tilt angle, right? And that's what you see. So these are the two resonators over this plus or minus 90 degree range of angles relative to the vertical. And of course, in this region, sine theta is approximately theta, you can extract a small angle linearized scale factor, which is what's reported there. The early devices, now compared again, even then, so that's a MEMS device right in the center there, where the laser dot is, against a industry standard seismometer and an industry standard gravimeter at the time for scale. And we had comparative measurements run and reported in a JMEMS paper about 8 years ago, which showed comparable response to that seismometer. But what we were limited by at the time was actually the background seismic noise in our labs. So the levels that we are measuring, in the sort of 3 micro-G per root hertz or so, was far above the electronic noise limited resolution that we independently measured. Though you can see some of the benefits of the VBA approach, which is the low frequency response, even then without an optimized setup. So one of the things we wanted to do next is to access a lab, such as this one here, which is in the south of France. It's an old Cold War missile site in the south of France that's now repurposed as a low noise lab. And you've got to go, a kilometer or more down these tunnels on bikes, or if you're lucky on the sort of tram-like thing, and you then get to a place which is far away from sort of the ambient seismic noise that otherwise impact on measurements. And this is myself and one of my PhD students debugging a circuit board. So so all of this was built up with discrete electronics, and it's incredibly hard to we spent about a week at this site. Incredibly hard when you're down in one of those labs to figure things out. But we did benefit from the fact that there wasn't that level of ambient noise around, and that started to focus our attention on other things, on the electronics, on the thermal control. And so electronics, we had worked on these front ends and these oscillator circuit interfaces for some time. This is a paper that reports on constructing compact models for MEMS oscillators that integrate nonlinearities in the resonator and in the amplifier loop, and understanding in a sort of an analytical form what that would do in terms of phase noise and frequency noise. So, as many of you might know, MEMS resonators, even at extremely low drive levels, can get well into the nonlinear regime. And if you're not careful enough, you could be operating in regimes where you have low frequency noise, up conversion, and other detrimental effects associated with that sort of operation. So modeling that's crucial, and you can see this in the response in the noise spectrum of these devices that are measured at different drive levels. So this was reported in IEEE sensors some years ago. So in the linear case, which is this black line here, you have a nearly flat response. As you go nonlinear, as has also been well established for oscillators, because it's essentially the same front end, you have benefits in terms of lowering the noise flow. You have this low frequency noise up conversion. So that's one part of the story, and sort of optimizing the front end is one part, and the operating plan is one part of it. The other part was improving the manufacturing process. This is now ported to an 8-inch production line. The process has differences, but essentially the same broad basis, which is 3 wafers that are bonded together in a stack. And these are fusion bonded in this particular schematic to create a vacuum down to the sort of millitorr level or so for these resonant MEMS devices with through silicon vias that allow for electrical interconnect to the device. And there are other variations around this that allow us to scale the dimension a little bit, but that's the broad basis of the device I'll be talking about to follow. So once we applied these combination of techniques, we started to pick up teleseismic events. And this is now a time frequency plot, acceleration on this vertical axis, frequency on that axis, and time on that axis. This was when we were out at a low noise test facility in Bristol. We've got a basement facility at the Nanoscience and Quantum Information Institute. And I was fortunate, in fact, we didn't even know that our instrument was recording, and back when we heard the news, and were able to then correlate this with a BGS seismometer station that was located about 25 kilometers from our monitoring site. So in terms of the signatures, particularly at low frequencies, you're now looking at signatures that are in the 10 to the minus 2 volts or so. These are not, or would not have been picked up by more conventional MEMS accelerometers. Okay, there's another piece of the puzzle, which is dealing with environmental noise in the terms of drift to temperature and pressure fluctuations. We published this about a year or so ago, but a lot of the experiments were done much earlier, and it just took us a while to put the paper together. But these were done in a environment where we're controlling for temperature. We are actively monitoring pressure in the ambient of the MEMS device. And even though the MEMS device itself is vacuum sealed, ambient pressure fluctuations can couple in as die stresses through the anchoring and such. And so what you think you're measuring as low frequency noise or drift is in fact just an environmental response. So what we see here is a very close correlation between the frequency drift of the device and the fluctuations in pressure levels that are recorded by an external MEMS pressure sensor. That's dominating the frequency drift in this device on these sort of time scales. And then if you correct for that, you see the residuals that are temperature dependent, and then you can correct for that as well. And that then required us to build in packaging to mitigate these effects. And part of that was to build a micro oven. So this is an Allen deviation plot of the temperature stability of the micro oven that was built up. This is one of the early implementations, but even then reporting a stability of better than 100 microkelvin on a time scale of about 20,000 seconds or more. So that's the sort of level of stabilities that are required to get down to the measurement regimes I'll talk about. So our early device, and this was still work that was being done largely at the university. The company had just about gotten going with one employee at the time, focused more on the tool and the system build I'll talk about later. This was run off benchtop measurement electronics. That's an image of the packet chip and the module that we were testing. And this is what we started to measure. So we start to pick up earth noise. So this is just due to the geophysical noise that you can measure in the order of about 200, 300 energy per root hertz. That's just due to ocean loading, ocean tides, and a noise floor at 1 hertz, about 25 energy per root hertz. And this is the Allen deviation that's reported here again in this scientific reports paper, showing a Allen deviation of about better than 20 nanoG on a time scale of hundreds of seconds or more. And when you get to these sorts of stabilities, you can start to track gravitational changes due to earth tides. That is the effect that the sun and the moon has on the gravity here on the surface. So these are the data against a theoretical plot of what the variation small g would be over a certain 4 to 5 day time course. Yeah.
Why is there a phase difference?
Yeah. So
you think they should sort of like nail where the moon is, right?
right. So it turns out that when you get small enough, it's not those are the dominant effects. They're not the only effects. So there are other corrections. For example, atmospheric pressure changes would have an effect. There are proximity to so you've got weather events in the proximity that can have an effect on the water level, the seawater levels, and okay. So you get you start to measure everything, which is why you see a bit of a difference. But the correlation is still pretty good.
Correlation is great. That's great. The amplitude's a little different. I just don't expect the phase to actually.
Right. So you add those other corrections, right? So one of the advantages here is that this particular device, as I said, can measure over the entire 1G dynamic range, and that's a particularly useful feature here on the surface of our planet. And yeah, we started to take off this instrument recording in different low noise locations. So this is a location way up in Scotland, again in the British Geological Survey observatory up there, with a seismic vault. Actually, we picked up a much smaller magnitude 2.6 earthquake proximal. This is another one. This is now the instrument back at the university in a noisier environment, but because of the instrumentation that we built around it, we're now able to measure these long period oscillations that you can see on time scales of fractions of a minute that are associated with the seismic waves that are picked up in Cambridge from an event in Mexico. So the company sort of scale up around the same time. So this is the compaction of the electronics with the resonance tracking now built on an FPGA. And most of this now is in the digital domain. And this helped with some improvements in noise floor down to the sort of 10 nanoG per root hertz, and stabilities. Now they're measuring over many runs. So this is many runs overlaid one on top of each other over periods of many days, and then we can start to put this to the paces as a useful field instrument. So one of the things that was done is to build a rig that you can dial in measurable effects of gravity change in a laboratory setting to rather than waiting for the tides, right? So one of the ways of doing this is just to look at the effect of elevation. So elevation, if you move up about a meter, depending on where you are on the surface of the planet, that's about a 300 microgal change or 300 nanoG change in gravity. And this is measurable. So by building an elevation rig that takes this up, over this distance and does it to a high level of precision, you can dial in a known gravity change. And these are the results. So this does line up, and what you see overlaid on top is the tidal effects that right on top of that. The gravity repeatability in these measurements is on the level of 6.5 microgal or 6.5 nanoG roughly. And of course, you can take off the tidal effects by knowing the model for earth tides. So this led to sort of a pre-production prototype that Silicon Microgravity has put together. And see some of the specifications for that initial prototype. So still fairly large, though the potential exists to compact the system significantly, obviously. Still run off discrete electronics that takes up most of the volume. And the initial application that Silicon Microgravity started to look at in collaboration with other partners was in geotechnical surveying. So this is, for example, in the context of large-scale projects like one of the projects in the UK known as HS2, a high-speed 2, as part of the high-speed rail network, where there's a lot of underground infrastructure that's being constructed, and you need to know where the existing underground infrastructure lies. So figuring out, the presence of voids under the surface is something that can be done using a gravimeter. Also, in terms of looking at breaks in pipes and cables, because if it's large enough in diameter, you can detect, if a fluid's present or not present, and so on and so forth. So this was the initial application that we started to look at. And there is a purpose-built facility for testing for geotechnical surveying called the National Buried Infrastructure Facility at Birmingham, where the gravimeter was taken out. So there are features, I better plug things in. So there are features like this one, which is a tunnel that is, in the form of a shallow a pipe that's buried a fraction of a meter under the surface. And, what you have with that is a model gravity response that would look like this. So a total gravity anomaly, as you took your instrument and you scanned it across the surface here, you went like that horizontally, you would measure a gravity anomaly, which at the peak here at the center is about 40 microgal, right? So 40 nanoG. And this is what we actually see in practice, okay, with CG6, which is the industry standard gravimeter. So you see, sort of a matching, including the matching of the asymmetry picked up in both systems, and the same sort of level of anomaly. So yes, where is this heading next? So compact gravimeter which is robust enough, can be mounted on a moving platform. So a drone or a rover, and that's part of what the company's engaged with through a funded project at the moment. As I said, one of the first applications was to monitoring fluids in underground reservoirs, and the company actually built up a tool that was reported on at the AGU fall meeting in 2019, and tested this tool in a variety of locations in the UK, down mines, and then in Canada for an initial baseline test. So this is the Aquastor CO2 capture project in Canada, where CO2 is being injected over a time course that's now continued for many years. And though because of COVID reasons, travel shut down, we couldn't go back because you need to take repeat measurements. There was a lot of modeling done to show the viability of borehole gravity measurements to monitor CO2 storage. So these are the results from the modeling. This is depth, true vertical depth. And this is the gravity anomaly, GX, GY, GZ, for the three components of gravity. And what you see is measurable changes. So we're talking about measurements on the level of 40 microgal. These are on the level of about 20 microgal or so. So well within the levels of performance of the instrument. And the way you would use these measurements is to, shown here, these are, for example, time-lapse measurements conducted over certain time intervals. So you go take a measurement at one time period, come back a year later, or a year and a half later, take another measurement, compare the differences between the two measurements, and relate those differences to the changes in the fluid densities in the reservoir. And these changes are on the order of tens to 20 microgal or so. Interestingly, if you could build a vector gravimeter, so 3 components, so there were 3 orthogonally mounted sensors in this particular tool, then you can also not only talk about the presence of a certain fluid, but also the directionality in which the plume's moving. For instance, whether it's in this particular case headed northeast because the gravity signals increase in that direction until they hit the well.
So
Yeah.
you're scanning this thing vertically and making
So
measurements as you.
so you can either have a set of sensors installed permanently and you're measuring continuously, or in this particular case, the tool's being lowered to different depths and it's left to measure for a certain time period at each sort of measuring interval.
And the CO2 is denser than the surrounding, or it adds to the density, or how does it affect that?
Yeah, it depends on what fluid's being displaced. But for example, at that depth and those temperature conditions, CO2, again, depending on what it precisely is, might have a density of about 0.7 grams per cc or so. And that, in contrast to say water that it's displaying, would have a measurable density contrast.
So less dense.
It's less dense in certain model scenarios, but depends on the particular conditions of that. That's important to tell. Right. So fast forward to right now. So this is what the current SMG module is displaying in terms of Allen deviation as of a month, maybe a couple of months ago. So this is now down to about 2.6 microgal at 200 seconds. And this is all the way out to 1,000 seconds or so, heading, I believe, ultimately push well below the nano G figure. This is the noise spectrum now down to 10 to the minus 3 hertz, so pretty flat, about 35 microgal per root hertz noise level in the instrument, and this instrument, of course, will measure, if you increase the bandwidth, measure all the ambient seismic that exists at higher frequencies. So that's the microseismic peak here at lower frequencies, but all of this is the ambient seismic in the lab. So that's micro G per root hertz over there. Right. So the company is planning to release first products next year. The initial would be something that would be used for those sorts of geotechnical surveying type applications, where these initial specs are still fairly large, but the potential exists to compact the system substantially in future iterations. And there is work on mobile platforms, on gradiometer configurations. We have 2 stacked systems, one on top of each other. So that's where the company is headed. Now, in the research domain, this is getting back to your question, Chris, on the details of the device and the mode localized sensor. So this was published earlier this year. This gives you a lot more detail in terms of how that will look like. So in fact, this could be used in both frequency output configuration or in a mode localized sensor configuration, which is what's shown here. But this shows the details of the drive and sense electrodes, and the coupling is in fact through the anchor. And it's the coupling for these modes where you don't get stress cancellations through the anchor. It turns out that you could have incredibly weakly coupled systems with this sort of configuration. The modes of interest of a study in the paper were these sets of modes down here, or these higher order modes up here. And these are some of the results from the mode localized sensor. So now down to a level Allen deviation of 75 nanoG, picking up microseismic noise in the background as well, the mode localized accelerometer, which is a first. And we pick up seismic events. This is a small earthquake in the UK, actually. I think it was, I don't remember what magnitude it was, but pretty small. But again, similar signatures to a seismometer station not far away. So it's been a lot of fun, and I have a lot of people to thank, including everybody in my group who are listed here who directly contributed to this work, and the collaborators, including Roger Howe, who many of you know, and who was my PhD advisor. So with that, and with this photo, this was back in the early days when we were going up to this facility up in Scotland, British Geological Survey site, showing some of the early members of the team, most of whom were at the university, apart from Philip, who was our first employee in the company. So yeah, and thank you. So look forward to your questions and interaction.
Well, Ashwin. Great.
Really amazing. Congratulations on all this hard work to get to where you are. I was thinking as you showed things like the tunnel detection. So how does like graviton? I would expect that there's other like active probing techniques like using acoustic waves,
Yeah, sir.
or like ground penetrator, radar.
Right.
And
They all
so
suck.
yeah. So that's maybe you can comment a little bit about that.
Right. No, absolutely. So there are these other techniques. So ground penetrating radar doesn't get you very high resolution, not very far enough underneath the surface. Gravity can sort of visualize, depending on how large a mass it is or how large a void it is. You can potentially see tens to hundreds of meters below the surface with the sorts of resolutions I've been discussing here. And it's all a passive technique. So unlike seismic, where you need some sort of active source, there is none. And seismic is also in direct measure. It's you're relating it through the properties of the rock that you need to know a little bit about. Though there's of course been a lot of energy around seismic and seismic interpretation. It's more in direct measure of mass, which gravity directly measures.
I wanted to ask about your DTF compact model.
Yeah, the modeling.
Can you repeat the question?
Oh, sure.
Yeah, well,
Sure.
figure.
Sure. So the question was on the modeling of the DETF or any other resonator. So there's a whole suite of techniques, right? So our CAD tools that we commonly use, COMSOL, multiphysics, for mechanical modeling. And so we look at things such as eigenmodes and dissipation mechanisms, and we look at you can look at localization effects and things of that sort. Now, so you can import CAD into COMSOL and run 3D models. You can also in COMSOL do pretty interesting things these days with not just the MEMS device, but you can include impacts of packaging, for instance. In terms of the we do rely at the early stage on analytical modeling as well, which I think is perhaps so to build that insight. I think it's very useful where you can, using also complementary tools like MATLAB, simulation software like MATLAB or Python, whatever what's your tool of choice to complement any simulation of the dynamics of the system. But yeah, those were probably what we tend to most commonly use in terms of software, if that's your question.
Circuit simulation?
Yeah, so circuit simulation obviously has got then its own set of tools. So you would, so SPICE or versions of SPICE and so forth. So you'll be capturing some abstraction of the resonator coupled resonators or whatever, where they're linear. Yeah. Well, yeah, obviously any model is a simplification of the real thing. So it depends on what level of abstraction you want to get into. So yeah, I mean, we've done, obviously not covered here in a lot of detail, but we've done a lot of work on nonlinear MEMS devices as well, where we've used, again, a range of different levels of modeling. So numerical simulations that we run in something like a MATLAB or some work that would complement what we're trying to look at in COMSOL or so, but it's typically very specific. There isn't that's one of the limitations that exists in MEMS design today is you don't have a general purpose CAD tool that can do everything for you. So the human is very much in the loop, and until that changes, that's part of the challenge.
Question?
No.
Okay.
Can you talk a little bit more about the device and I think you've had a cross-section. You talked about having 3 wafers, but I think it kind of explains a little bit faster. We can go back.
Sure. Yeah, so the question was to describe the fabrication process in a little bit more detail. So essentially, we have 3 wafers that are bonded together. You can think of the lower wafer being the electrical interconnect wafer, where the through silicon layers are built in, and the bond pads on the outside. So that wafer is bonded to a second wafer, which starts off being an SOI wafer, but the handle is sacrificed. And so we work with we build our devices into that second wafer device layer. And then there is a third wafer that's bonded onto that stack in a vacuum. Fusion bonded in a vacuum, for instance, to create our vacuum packaged wafer and vacuum packaged sensors.
It's about 7 minutes over time, so I want to end today's seminar. Let's thank Ashwin again. Okay, our lunch at the backside, especially for students to pick up the lunch.